All right, so you're motoring through and you're already on 2.4 in this unit. So that's our third lesson. We're looking at multiplying and dividing radical expressions now. So in the first lesson, we looked at multiplying and dividing radical expressions, but not kind of together. We're just looking at within a radical, how can we break it up and put it back together. Now we're actually looking at two separate terms that we're trying to combine. So when you multiply radicals, okay, so focusing on multiplying first, okay, we multiply the coefficients and you multiply the radicands. Okay, so again, radicands are underneath the radical. This only happens if they have the same index. So we see this when we do the root 3 multiplied by root 5. What that is actually equivalent to is root 3 times 5, or the root of 15. Alternately, if we look at these two terms here, we've got 2 times 3 is 6. We multiply the coefficients, 2 times 3. Then we multiply the radicands, so we're dealing with root 3 times 3, which is actually root 9. Now, watch out, because what happens here is that we can take the square root of 9, so we can simplify this further. 6 times 3, or 18. So always check for that simplifying piece that we were doing in the previous lessons. So what's a scenario, before we move on actually, what's a scenario that we would run into where we can't do this? Well, a non-example would be if we had the square root of 3 multiplied by the cube root of 2. This cannot be simplified. And the reason is we must have that same index. So those not matching indices means we cannot do this. So expand and simplify for each of the following. We've got root 2 multiplied by root 6, so that's root 12. But 4 goes into 12, so that's going to be 2 root 3. So again, thinking about it as root 4 times root 3. And then simplifying this part. Square root of 3. Now, in this scenario, we are going to have to distribute. Okay, so just like any other monomial times a binomial, when we have a single term multiplied by two terms in brackets, we need to multiply both pieces. So we're going to have root 3 times root 3, which is root 9, minus root 3 times root 7, which is 21. This one's not going to be simplified, but 9, the square root of 9 can be, so we end up with 3 minus the square root of 21. So when I'm checking for simplifying 21, always remember you're looking for perfects. So we're taking the square root, so you're looking for perfect squares that can go in there. For C and D, we're using that same distributive property, but it's two binomials. So what we're actually looking for is, or binomial, two-term multiplications. So we're essentially going to FOIL, just like we did with polynomials. So we've got 4 times 3 if we're doing our firsts. 4 times 3 is 12. Root 2 times root 2 is root 4. Okay, if you can spot right away that that's going to simplify to 2, you're more than welcome to rewrite that. You're more than welcome to rewrite this whole term as 24. I'm just going to take some steps to do that. Okay, so then outsides, 4 times negative 1 is negative 4. Root 2 times root 5 is root 10. Then I've got insides, so that's going to give me 2 times 3 is positive 6. Root 5 times root 2 is root 10 again. And finally, getting back to my lasts, 2 times -1 is -2. Root 5 times root 5 is the root of 25. From here, I definitely want to simplify. I want to look to see if my radicals are going to simplify at all, like if I can take square roots of anything or find perfect squares within them. I'm also going to look for like terms. So you're looking for two things. Perfect squares, and you're looking for like terms. So root 4 is actually the same as 2, so 12 times 2 is 24. These two pieces are actually like terms, so -4 plus 6 is plus 2 root 10. And finally, the root of 25 is 5, so 2 times 5 is 10. We're not done though, because we still have some like terms now. We've got two constant terms, so we can combine those. So we can end up with 14 plus 2 root 10. So pause the video right now. Why don't you try this one on your own? So when we go to simplify this particular two-term or four-termed multiplication, depending on how you count them, what you might notice to start off with is that we are dealing with a difference of squares. So we've got opposite signs, but otherwise our terms are exactly the same, which means that when we actually FOIL this out, our middle terms are going to cancel. Now, because we can simplify these radicals and they end up being squared, so the square root of 2 times the square root of 2 is actually 2. The square root of 3 times the square root of 3 is actually 3. We actually end up with whole number value as our final answer. So watch out for those difference of squares. They can actually help you in terms of giving you quite a simple answer, despite the fact that they look quite complicated to begin with. So when we introduce a variable radicand, we must identify the values where it is restricted, so where it's going to be defined as the alternate piece. Any restrictions on the variables must be determined from the original expression. And so you'll notice that I've already been doing that in the previous lessons. I've always looked at the beginning, the question, not necessarily the answer. So if anything disappears, it's still technically accounted for from the original question. Just because you've simplified it doesn't mean it's completely gone away and that we can ignore those restrictions. So as it points out here, why are there no radicals in your answer for D in the previous example? We are dealing with a difference of squares in that case. So you can keep an eye out for those, and they always simplify pretty nicely. So we're going to come across that in A. So we've got 2 root x times 2 root x, aka 2 root x squared. That gives me one of two ways of looking at it, either 4 root x squared, or you could just simplify that directly to 4x. Then I've got -5 times 2 is -10, but I've also got 5 times 2, which is +10. So those are going to cancel. Again, noticing that these are difference of otherwise square terms. Okay, so I'm going to skip those insides and outsides, and I go to my last, it's going to be -25. So my final answer is actually going to be 4x minus 25. But I still have my restrictions from my original question, which means that anything under my radical cannot be 0, or it cannot be negative. So I've got x must be greater than or equal to 0. Unfortunately, B is not a perfect square, so we are going to have to deal with this full on. So first, 7 times 3 is 21. 7 times negative 5 is negative 35 root b plus 6 root b minus 10 root b squared. Again, remembering that this will simplify to just b and that we can collect like terms. Finally, we're left with a negative 10b minus 29 root b plus 21, and that will be my final answer. So you were about to move on to question C for this example, but you forgot one little thing. We still have to state our restrictions for B. So remember that B in this case would have to be, again, greater than or equal to 0 because we can't take the square root of a negative. C looks intimidating, I will agree, but bear in mind, you already know how to do this. It's just going to take a little bit of space. So first we're going to deal with just our front term, looking just at that. Don't get scared off by what's in behind that after. We'll deal with that in a second. Okay, so we're dealing with a difference of squares. So I'm not going to have that middle term, so I just need to take my first and my last. So that's going to be 9 root x squared, and then plus, no, not plus, minus, don't forget those are opposite signs, the square root of y squared. We are then going to subtract all of this squared. Now, when you square a binomial, can you substitute and just apply the square into everything? No, do not do that, because remember what this square actually means is it's multiplying by itself. So by just squaring each individual term, you are forgetting those middle terms. And unfortunately, because these have the same sign, they are not going to cancel out. So we are left with the square root of x squared plus 5 root xy. Okay, so still multiplying everything under the radical, plus 5 root xy, and you don't need to keep them in the same order that they're written here. So yx, xy, same thing. And then finally 25 root y squared. So you can do a couple things at this point. You can either choose to distribute this negative indirectly, or you can simplify this back set to start with. I'm going to simplify because I like it when things are simple. I'm even going to simplify these first two terms. So the square root of x squared is x. Well, I'm actually dealing with 9x minus y. And then I'm subtracting x plus 10 root xy plus 25y. Now that I've got my terms as simplified as I can up to this point, but I still have an x term in and outside the bracket, I've still got a y term in and outside the bracket. So I'm going to take that negative and I'm going to distribute it into all three terms. So then I can change my signs. It's going to be subtracting and subtracting, and I'll be able to simplify from there. So I got 9x minus x is going to be 8x. Negative y minus 25 is minus 26y. And then I'm subtracting 10 root xy. But again, I'm not done until I actually state my restrictions. So x and y need to be greater than or equal to 0. And that'll be my final answer. So it looks scary when you first see the question. Absolutely, it's going to take up some space. It's going to take some brain power. It's going to take a lot of remembering from our polynomial unit. But it's still manageable. It's still applying the same skills that we used in A and B when we see a question like C. So that's multiplying radicals. Dividing is a little bit trickier. So the first thing you need to remember is that when a fraction is multiplied by 1, its value doesn't change. So for example, if we've got 4/5, and we multiply that by 3/3. Remember, anything divided by itself is 1, so this is technically 1. So we're multiplying by 1. What ends up happening is that we get an equivalent fraction, but that we could then reduce it to 4/5 again. So it's actually still the same. So we use this idea of multiplying by 1 when we're trying to simplify radical expressions, when we're dividing radical expressions, because what we actually want to do is we want to get rid of that radical in the denominator. So we call this rationalizing the denominator. And what that is getting that, canceling the radical in the denominator. Cancel is not the best word. Maybe just eliminating. So how this works is we've already seen the math involved, because when we square a square root, those operations cancel each other out or undo each other, and they end up giving us just the number that's underneath, that radicand. So let's see what this looks like. To rationalize a denominator, what I would do is I would take my original fraction or division, and I would multiply it by 1. But I'm not going to actually put 1 here. I'm not going to put a whole number because that just ends up in front of the radical. I want to square this to get rid of it. So what happens is I'm going to multiply by root 2 over root 2. This is still 1. The resulting fraction is that I get root 2 over root 2 squared, which is just 2. Now it's rationalized. That is my simplified answer. So where do we use this? Well, we can use it in all of the following questions. In this case, what would we multiply by? We need to cancel out root 7, so we're going to simplify root 7. So that's what we're going to square, quote unquote, by multiplying by 1. My denominator is going to just be 7 now. My numerator, because I have 2 terms though up here, I do need to multiply them both. So that means that we do have that element of more than one thing multiplying together. So I've got 5 root 7 times root 7 is 5 times 7 plus 3 root 7, which I can rewrite as 35 plus 3 root 7 over 7. Now, one thing I cannot do is I cannot just go, okay, well, 7 goes into that evenly, so that's actually going to be 5 plus 3 root 7. That doesn't work. Okay? Because 7 is dividing both terms, it needs to be accounted for in both terms. It can't just cancel out of one and then disappear from the other. Okay, so leaving it in this answer form, is actually totally fine. Okay, in the example for B, you could multiply by 2 root 3, but then we're going to be dealing with some potential canceling out. What I'm going to do is I'm just going to multiply by root 3 over root 3, because all I need to get rid of is my radical. I don't care about that whole 2. It's already a whole number. It's fine in the denominator. All I need to get rid of is the radical. So in my denominator, that's going to be 2 times 3 now. Again, I'm going to have to apply my numerator to both pieces. So that's going to be 2 times 3 plus root 3. From here, I'm going to simplify 6 plus root 3 over 6. Again, I'm not able to cancel there because this denominator applies to both pieces. If you wanted to, you could hypothetically write this as 1 plus root 3 over 6. That would be totally acceptable. Both of these are legitimate answers. But that denominator needs to stick around with the root 3. It doesn't cancel out with any coefficient there. C still fits in the same bill. I'm just dealing with a radical in the denominator. So I continue to multiply by 1. I'm going to have to apply it to both pieces in the numerator. But root 18 is going to be relatively easy. You could simplify root 18 first, and actually I'm leaning towards that might be what I do, just strictly because, like I said up here, I like to deal with simplest form as early as possible. So before I do anything else, I'm going to rewrite this as 6 root 2 minus 4 root 3 over 3 root 2. Now that happens again because 18 can be broken down into 9 times 2. Well, 9's a perfect square, and I can actually break it down and write it as a mixed radical instead. From here, now I'm dealing with just multiplying by root 2 over root 2. That's much more manageable than dealing with 18, and especially since I don't have a calculator, I don't want to have to deal with bigger numbers if I don't have to. So I'm going to multiply my denominator, and that's going to give me 3 times 2. My numerator is going to be 6 times 2 minus 4 root 6. Now, as I continue to work through this, I've got 12 minus 4 root 6 over 6. In this particular case, we actually do run into a scenario where we can simplify this because all three pieces, 12, 4, and 6, all have a common factor. And so my final answer here can actually be 6 minus 2 root 6 over 3. I can take 2 out of all of 3 terms. So that's what simplifying can look like, bringing it down into your lowest form. Now, what we were seeing up there, these are all monomial denominators. Down here, what happens when we end up with a binomial denominator? Well, we still want the radicals to disappear from the denominator. But in our case, we are going to need to use the conjugate now, what we call the conjugate. So this application is a difference of squares idea. That idea that that middle term goes away, so the radical should go away too. So the conjugate of a plus b is a minus b. So all you do is change your sign. So the conjugate of 5 plus root 2 is 5 minus root 2. So what's the conjugate of 2 minus root 6? That's going to be 2 plus root 6. What do you think the conjugate is going to be of root 2 plus 3? Well, you've got a couple options. Either you can write it as root 2 minus 3, and that's actually your best option. We could hypothetically rewrite it as negative root 2 plus 3 and change the sign of the first one, but that can get kind of confusing. So changing the interior sign is always your best bet. Okay, so let's see what this looks like. I need to multiply to rationalize, so I'm going to multiply by 1, but I need to use my conjugate because my denominator is now a radical, or a binomial. So I've got 3 root 2 plus 4. 3 root 2 plus 4. Okay, So this is going to be a little bit of a monster because I've got a binomial times a binomial in the numerator. So it's going to be firsts, so 12 root 2. Outsides is 16. Insides is 6 root 12. And lasts is 8 root 6. All divided by 3 times 3 is 9 times 2 and minus 16. And again, I can skip those middle terms because I'm dealing with a difference of squares. So I'm looking here and I try and see if there's anything I can simplify. 12 breaks down into root 4 times 3. Root of 4 is 2, so I'm actually going to have 12 root 3 there. But other than that, I can't really do much in any of those terms. So I've got 12 root 2 plus 16 plus 12 root 3 plus 8 root 6, all divided by 2. Can 2 go evenly into all of these terms? Well, it can go into 12, it can go into 16, 12, and 8. Yes, lovely. So what I can actually do is I can finish this without having any denominator by writing 6 root 2 plus 8 plus 6 root 3 plus 4 root 6. So again, using the ideas from previous years, previous lessons, previous units, that we want to simplify as far as possible. Now, why can't I simplify that anymore? Because my radicals are all different. Next example. Feel free to pause the video at any time and try on your own. We're going to be dealing with 3 root 2 minus 2 root 3. So my denominator is going to be 9 times 2, subtract 4 times 3. My numerator, I'm going to have 6 root 6 minus 4 root 9 minus 12 root 12 plus 8 root 18. Okay, so I've got lots of simplifying I can do here. 9 becomes 3. 12 breaks down to root 4 times 3. 18 breaks down to root 9 times 2. Okay, so lots and lots of simplifying. 9 times 2 is 18. 4 times 3 is 12. So we're going to end up with 6 root 6 minus 12 minus 24 root 3 plus 24 root 2 all over 6. Again, it works out nicely that 6 goes evenly into all of these terms. So we're left with root 6 minus 2 minus 4 root 3 plus 4 root 2. I can't go any further because all my radicals are different, so I'm done at this point. So you've got lots of practice questions. I definitely recommend spending some time on this idea of multiplying by the conjugate, making sure we're still foiling, looking for those perfect squares that we can simplify. Definitely do some practice questions here before you move on to our next lesson.